Let's get started. So, hello everybody. My name is Cameron Braunstein. I am a master's student here at Saarland University in Data Science and Artificial Intelligence. And for my master's thesis, I am conducting some research into quantum machine learning. So this quantum computing survival guide really came about as I was getting up to speed on quantum computing, and I felt like I really wanted a resource that was both mathematically rigorous, but also did not require a physics degree to understand. So this is really a presentation by somebody who has more of a computer science background for other people with more of a computer science background. So the first natural question to ask is, what is quantum computing? And we will define it as the leveraging of quantum physics to perform calculations. And if we are clever about how we set up our quantum experiments, we can we can perform certain calculations significantly faster than on a classical machine. And for this presentation, I will focus exclusively on one paradigm of quantum computing, which is on gate-based quantum computing, which involves performing computations on quantum circuits. So the goals of this presentation are threefold. I want to give you a thorough explanation of the foundational mathematics governing quantum circuits, with aiming in the direction of introducing you to quantum machine learning, abbreviated as QML. I want to demonstrate these explanations with code examples using Pennylane, which is a Python library meant to simulate quantum circuits that's really geared towards QML. And I want to equip you with sufficient working knowledge such that you could look at a QML research paper and understand what they are actually talking about and feel grounded and know what's going on. So this presentation is split into three parts. First, we will explore single-qubit circuits. Then we will take the lessons that we learn in that realm and apply them to multi-qubit circuits. And then I will close with more of an overview introduction to quantum machine learning. And to break down this single-qubit circuit topic into some subtopics, I first want to tell you what a quantum circuit is. Then I will explain to you what a qubit is, followed by how we make quantum measurements. I will then explain how we will process quantum data using quantum gates. And then we will take a sort of intermission and think about how we can apply all of this technical information to think about single qubit circuits as computers. So a quantum circuit has the following pieces to it. In a quantum circuit, a qubit is altered by passing it through quantum gates. And finally, this altered qubit state is measured to be one of two states. And what we have here is a quantum circuit diagram. We can think of essentially the qubit as traveling from left to right and being altered. So initially we start with some qubit here psi. It will metaphorically travel along this wire and pass through a quantum gate. And then it will travel to be measured. And when we measure the qubit, we will observe one of two outcomes. So, what is a qubit? Many physical properties of particles can be modeled as a qubit. All that a qubit is mathematically is a two-dimensional vector where the entries can be complex numbers. And we require that a qubit satisfies this property here, that the modulus of the first entry alpha squared plus the modulus of the second entry beta squared is equal to 1. Now, some notation that you should have already seen is this raw ket notation. This was used in the quantum diagram. And this notation is really used for convenience when we are talking about quantum computing. So what is this notation? Well, let's say you have some vector psi. You can write it equivalently in this ket notation. So we just have this straight line psi and then this angle bracket. And if we want to write the conjugate transpose of a vector psi, which means that we take our vector, we transpose it, and then we take the complex conjugate of both of its entries, then we write it in this raw form where we have our angle bracket first, followed by psi, and then a straight line. What this notation allows us to do is very conveniently express inner products and outer products. So if we have these two qubits, psi and phi, in ket form, then the inner product between these two qubits is a bra followed by a ket, and this is actually what this will evaluate to. It's just a scalar value. And then the outer product between two qubits ends up being a matrix in the following form. So to show you why it's very helpful to have this notation, we can succinctly write our definition of a qubit as follows. A qubit is this ket in the two-dimensional complex space, and the inner product of the qubit with itself must be equal to 1. And I leave it as an exercise to you to show that this is equivalent to the definition that I introduced on a previous slide. So now that we know what a qubit is, we would like to be able to look at a qubit in a classical simulation. And to do that, we are going to use a Python library called Pennylane, which I really have come to enjoy using. As I said before, it's intended to be used for quantum machine learning research. They went to great lengths to really integrate it very smoothly with the PyTorch library for machine learning. And if you have the correct credentials, API keys, and so on, you can even integrate the circuits that you designed in Pennylane to use on actual quantum computers. So to introduce you to Pennylane, I want to do the simplest example I can think of, which is to show you how Pennylane initializes a qubit by default. And by default, Pennylane initializes all qubits to be the so-called zero ket. So that's defined here. You see it as this 0 inside of the ket notation. And all that this stands for is a vector with a 1 in the first entry and a 0 in the second entry. And now I'm going to jump over to my Jupyter notebook with Pennylane examples, and we will see how Pennylane models this. Okay. So on this top line, I'm just importing Pennylane and some other libraries that we will use later. This should not be too surprising. And here in this cell, I am defining my quantum circuit. So in order to do this, we need a little bit of syntax. So first we define a device here, which we will just use the default qubit simulator here. We will specify that our device has a single wire. And what this means is that we are only going to model one qubit. And then in order to actually define the circuit, we just write the circuit as a function. So in this case, it is default qubit state. And all that we want this function to do is return the default state. And so as you see, I've already run this, but when I want to print out what this function returns, you can see that it is printing out a 2-entry vector. Here we have a 1 plus 0j, so 1 plus 0 I, 0 in the complex entry, and then just 0 in the second entry. So Pennylane is working as we would like it to. It is just modeling the 0 ket by default. Now, what we've just done in Pennylane is it's physically impossible to do on an actual quantum machine. We cannot observe a qubit state directly. Instead, we are only able to measure a qubit. And in a circuit diagram, what you will see is the following. We have a qubit psi. We pass it through generally a box with this little dial symbol. And then we output one of two options that you can interpret as a classical bit. And this measurement will collapse the qubit into one of two possible states. And the initial qubit state that we started with on the left cannot be recovered. Now, there's a question of how we actually take one of these measurements, what we have to specify, and what the outcomes will be. And to take a quantum measurement, we will require a 2x2 Hermitian matrix A that we will need to specify to our quantum circuit simulator. In the remainder of this presentation, Hermitian matrices are given the letter capital A. And A is called an observable matrix. it will define the two possible states that can be observed, and it will also define, it will also give us the probabilities of observing one state versus the other. Just as an aside, if we're a little rusty on the linear algebra, a Hermitian matrix, also known as a self-adjoint matrix, is any matrix that is equal to its conjugate transpose. So here is an example of such a Hermitian matrix. So you can see that it's almost a symmetric matrix. However, the imaginary components on the off diagonals are negated with one another, as opposed to just taking a transpose. Now we need a little bit more linear algebra knowledge here. So to something that you may recall is that by the spectral theorem, we can, a Hermitian matrix has an orthonormal eigenbasis, and we can write our Hermitian matrix A as a sum of outer products of these orthonormal eigenvectors with themselves, with each outer product multiplied by the corresponding eigenvalue. Now, there is a rule that governs which states we observe and with which probabilities, and this is called Born's rule. So when we make an observation with an observable A, we will observe the qubit collapsing into one of the two orthonormal eigenvectors of the eigenbasis. So here we have a probability that we will collapse into the eigenvector AI, given our observable A and some qubit psi that we want to observe. And Born's rule states the following. Given these two elements, the observable and the qubit state, the probability that we collapse down into the state AI is equal to the inner product of AI with our qubit psi modulus squared. And it might not be obvious looking at this rule. However, I leave it as an exercise to you to prove that the measurement probabilities across all of the possible states that we can collapse down to will always sum to 1. Okay, I know that that was a lot of math, so I want to, and it was rather abstract, so I want to give a concrete example of how this will work. So we're going to go back to Pennylane, and we are going to measure the zero ket using what is called the poly-Z observable. So we'll define psi to just be our zero ket that we are familiar with already. And then we are going to define A to be this poly-Z matrix. In the literature, you will often see it referred to in the following way as the sigma subscript Z. And all that this is a matrix with the following entries here on the right. And the circuit that we want to create will just measure our default qubit state. And something to keep in mind is that when Pennylane is measuring and taking a sample, what the simulator will return and say to us is not the eigenvector that the qubit collapses to, but rather the corresponding eigenvalue of the measured eigenvector. So, okay, example 2. So I just want to contrast this circuit with the one that we have already seen. So here, when we're defining a device, we are adding this parameter shots and saying that there will be 10 shots. What this means is that we are going to run this circuit 10 times and measure the eigenvalue that we observe 10 times. And then in the sample poly-Z circuit that we defined, instead of just returning the state, we now return a sample on with the poly-Z observable here applied to wire 0. So I will define that. And something that's also nice about Pennylane is that you can draw these circuits that you've defined. So here is our very simple circuit diagram. We can see here our qubit number 0 is being initialized, passed through a wire, and then the circuit ends by taking a sample with the poly-Z observable. And when we print out what this circuit returns, we see that we get an array with 10 ones, so 10 samples, and each time the observed eigenvalue is 1. Okay, so why are we only observing ones? Well, if we take our observable matrix and our qubit and we plug them inappropriately into Born's rule, we can see that this is all mathematically consistent. So the poly Z matrix has an eigen decomposition as follows. We have the eigenvalue 1 times the outer product of the 0 ket with itself. And then we are adding to it the eigenvalue of -1 times the inner product of, or the outer product, excuse me, of the 1 ket with itself. And here, the 1 ket is just a vector defined as follows. It has a 0 in the first entry and a 1 in the second entry. So then, using this information, we just plug in the appropriate values. So we know that we will either have our qubit collapse to the 0 ket or the 1 ket. And then if we go through all the math, we see that we should expect that we collapse to the 0 ket with a probability of 1, meaning that we always observe the 1 eigenvalue. And the probability of collapsing to the 1 ket is always 0, so we're never going to see this eigenvalue of -1. So this was a bit of a boring example. We were always observing the same thing. So just to show you that we can get some more interesting observations, I'm going to change the circuit that I just showed you just by changing our observable. And instead of the poly Z matrix, we will now use the poly X matrix. And that is defined as follows here with the following entries. And I leave it as an exercise to you after this presentation to prove that this circuit should measure the eigenvalues -1 and 1, each with a probability of 1/2. And let's see if the Pennylane demonstration will back up my claim. Okay. Here, this circuit is identical to the one that we defined previously, except instead of a Z here, we now replace it with an X. We can see our circuit here. And let me just define this. And now, each time that we print what this circuit returns, you can see that our array of 10 entries is changing. And it doesn't have to be 50-50, but around half of the time, these entries are 1s, and around half of the time, these entries are -1s. So to make our qubits a little bit easier to work with, we are going to introduce a basis that we can write our qubits in, which will ease our calculations a little bit down the line. So we can write any qubit in terms of the Z basis form. So all that this is if we have some qubit psi with entries alpha and beta, we can write it as alpha times the 0 ket plus beta times the 1 ket. And we will see that this makes it very easy to determine the measurement probabilities if we are observing with the poly Z matrix. And what we can show is that the probability that any qubit will collapse to the 0 ket when we make a measurement with the poly Z matrix is equal to the modulus of alpha squared. And conversely, the probability that we collapse to the 1 ket is the modulus of beta squared. And I leave it as an exercise to you to prove that this is true using Born's rule. And because of this property, you may also hear of these coefficients alpha and beta referred to as probability amplitudes, because if you look at them, you can easily determine what the probabilities are of this qubit collapsing to the 0 ket or the 1 ket. A very important statistic of a single qubit circuit is the expected value. And all that the expected value is the average of the measured eigenvalues. And the notation that you will see when describing the expected value is as follows. So the expected value on some observable matrix A in these brackets, subscript psi, which is our qubit state before we make our observation, is just equal to the sum of each eigenvalue times the probability that we measure that eigenvalue. So I will just show you that Pennylane can also return expected values from us. This first circuit that I have here is just making observations of the 0 ket using the poly Z matrix and returning an expected value. You can see that in the circuit diagram, instead of saying sample Z, we now have a Z in brackets at the very end of our wire. And when we print the expected value, we always just get 1. And this should be reasonable to us because if you recall, whenever we made measurements using the poly Z matrix, we only observed the 1 eigenvalue, so the average should be 1. And likewise, if we take the expected value of our poly X observable circuit that we worked with before, we get an expected value of 0. And this happens because half of the time we were measuring an eigenvalue of 1 and half the time an eigenvalue of -1. Therefore, the average should be 0. So now that we know a little bit about measuring qubits, I want to revisit this question of what a qubit is and how we can represent it. So how many real numbers will it take to parameterize the qubit? If we think about a qubit just as a vector in this two-dimensional complex space, you would think, okay, I need 4 real numbers to represent this, this entity. However, remember that this qubit must be normal, the inner product of the qubit with itself has to be equal to 1. So this reduces the dimension of our space of qubits a little bit. So now we would only require 3 real numbers to represent any qubit. And we can parameterize any qubit in the following way with these real parameters, gamma, theta, and phi. So I won't spell out the notation, but you can see it here. We have this this phase on that's applied to both entries, and then entries as follows here. However, there is more to this story because there are classes of qubits that have different entry values which can yield identical measurement probabilities. And what you can show is that a global phase shift, which is here written as e to the I gamma, will not affect measurements. And what this means is that if you take any qubit, you multiply it by any global phase shift, which you can write in the following form. This will not change any of the probabilities of a qubit collapsing to one state versus the other. And so because we can only interact with qubits through measurement, for all practical purposes, these qubits are the same. And so we can just treat them as being equivalent. And I leave it to you as an exercise to show that that this global phase shift has no impact on the measurement probabilities. And you will have to use Born's rule to prove this. So we can make our representation a little bit simpler. We can simply factor out this global phase shift, this e to the I gamma that was present in our previous parameterization of the qubit. And what we are left with is that any qubit can be parameterized by two real numbers, theta and phi, that are in this range of 0 to 2 pi. Now, this parameterization here is not very intuitive to visualize or anything like that. So a tool that people use to visualize a qubit is something called a block sphere. And so what this does is it takes this qubit value and it places it on the surface of this three-dimensional sphere. And the way that we map the qubit to a specific point on the sphere is given by the formula below. Basically, if we have a qubit parameterized by a theta and a phi, we can take theta, we can take the qubit to be a point where theta is the angle between the qubit and the north pole of the sphere, and phi is the angle between the x-axis and the qubit here. Something that I just want to emphasize is that these block spheres can be very helpful visualizations. However, these coordinates are different from the Ket representation that we've been working with up until now. It's very easy to get these confused and get sort of stuck in the mathematics. So to give some examples of what I'm talking about, we can represent the zero Ket as being at the north pole of this block sphere. And if you remember, the zero Ket is this two-entry vector with a 1 and a 0. However, the block sphere representation gives us these coordinates of 0, 0, 1. And also the 1 Ket is here at the south pole of the sphere. But remember that the 1 Ket is actually this vector with entry 0, 1, but it has the coordinates as if it were the south pole of the sphere. Now that we know a little bit about qubits and how they're measured, we actually want to manipulate them in some way. So we can alter a single qubit by metaphorically passing it through a quantum gate. And every single qubit quantum gate is defined via a 2x2 unitary matrix V. So in a circuit diagram, what you will see is we have our qubit state. We have it travel along this wire, again, metaphorically, and it will pass through this square in the diagram, which represents some sort of quantum gate where we change the qubit, and then it can continue on to be measured. One last thing. So whenever I am referring to a unitary matrix in the remainder of this presentation, I will try to use the capital letter B. And also, so that we are all on the same page still, I want to give a reminder that a unitary matrix is any matrix whose inverse equals its conjugate transpose. For an example of a unitary matrix, I will introduce the third and final Pauli matrix, which is the Pauli Y matrix, which is defined as follows. What's crucial to us about unitary matrices is that they will preserve the vector norm. And what this means is that if we multiply a qubit by a unitary matrix, we will the product that we get will still be a qubit and obey its definition. I'm jumping ahead a slide or two. Yes, so to apply a quantum gate, we simply transform the qubit with the unitary matrix. So if we have some old qubit state psi, we apply a unitary transform B to it to arrive at our new qubit state psi prime. Yes, and I leave it as an exercise to you to show that because the unitary transform preserves the vector norm, then this qubit on the left, psi prime, is still a qubit and obeys our definition of being a qubit. Now, I want to take this example that I just described and show it to you in Pennylane. So what this circuit will consist of is our initial state of 0 ket, just like always. We are going to pass this qubit, the 0 ket, through the unitary matrix, that is the poly Y matrix. And then we will make an observation of this qubit using the poly Z matrix. And in quantum circuit diagrams, you will see the poly Y matrix written as follows. Okay. So here at the bottom, we have the circuit that I just described. The only thing that should be novel about this circuit is that we are applying this poly Y matrix here in the middle. I'm specifying that it's being applied to wire 0, so our only qubit. You can see that when I draw the circuit diagram here at the bottom, that it is as we expect. We are passing it through this Y, and then we are finally sampling with the poly Z matrix. Okay, and when we print out what this circuit returns, we see that we have an array of all negative ones. And just to prove that this isn't just a coincidence, I will define things. And now I will run the circuit many, many times. And you can see each time I print out the output, it's always just negative ones as the measured eigenvalues. So I want to visualize this transform and try to explain a little bit why we are only getting these negative ones. So I'm going to use this block sphere because remember that the whole point of the block sphere is to be a visual tool, so I should make use of that. So when we start, our circuit has our value of psi equal to the 0 ket. So our qubit is living on the north pole of this block sphere. And then what's happening when we apply the poly Y matrix is we're actually rotating this point 180 degrees around the Y axis of our block sphere. And then we end up with a psi prime of 1. And because of this, whenever we make our measurements with the poly Z matrix, the eigenvalue that we observe will always be negative 1. So let's understand this mathematically, what's going on. So if we take our formula from before and plug all of our known variables in, what we get is that our new qubit value should be the product of this vector and this matrix. Therefore, if we evaluate that, we see that our new qubit state should be the following vector with entry 0 and I. But then remember that we can multiply this vector on the left by any global phase shift, and one such global phase shift would be negative I. Or we could think of this as just factoring out an I from both entries. And then what we are left with is our familiar 1 ket form with the 0 in the first entry and a 1 in the bottom entry. Okay, I want to now expand a little bit on this idea of quantum gates and introduce parameterized gates to you. So instead of having a gate where it's just a set transformation, perhaps we can change the qubit state gradually with respect to some parameter that we can tune on the quantum circuit. So I'm going to call this tunable parameter theta, and I'm going to now create a quantum circuit that is almost identical to the one that was just shown. However, instead of using the poly Y matrix, I'm going to use this Y rotation matrix. And the entries of the Y rotation matrix are parameterized as follows by this parameter theta in the range of 0 to 2 pi. So I have me define this circuit. It should be nothing new, except we now have this Ry as our gate. And for illustrative purposes, I specified a theta of 0. I just needed to put something there so that the diagram would be drawn by Pennylane. But now what I want to do is see how the expected value of this circuit changes with respect to this tunable parameter theta. So I've just previously written some Python code which should take the expected value of the circuit from thetas between 0 and 2 pi. And I want to graph out what happens. So I won't run it again. It will produce the same output. But what we can see is that when we are graphing this expected value, we get a sinusoidal function. Now I want to visualize how the qubit is changing with respect to our parameter theta on the Bloch sphere. So if we start at the North Pole as before, and we have a theta equal to 0, then we can show that our y rotation matrix just is equivalent to the identity matrix. So nothing is changing here at the top. Psi prime is just equal to psi. However, as we vary theta, let's say we go to pi over 2, our y rotation matrix will actually take our qubit state and rotate it 90 degrees around the y-axis. And then if we set theta equals to pi, we can actually show that our y rotation matrix is equal to the poly y matrix. And we know from before that this is going to rotate our qubit 180 degrees around the y-axis. So what we can learn from this is that the y rotation gate will rotate the qubit around the y-axis of the Bloch sphere by an angle theta. And you can pat yourselves on the back. Congratulations. You've managed to model a sinusoidal function using a quantum circuit. So first, perhaps slightly practical application of a quantum computer so far. And I leave it to you to prove that the circuit actually calculates the cosine of theta. It's a little bit more involved because you have to consider what expected value measurements do, but it should evaluate to the cosine of theta. One final point I want to make about quantum gates is that multiple gates can be applied in succession, and the qubit will undergo each unitary transformation in sequence. So if we have a qubit psi that we first pass through a gate with unitary matrix B, and then we pass it through a gate with the unitary matrix C, then the way that we state this mathematically would be we have our old qubit here on the far right, and then we multiply it by B, and then by C, and then we get our new qubit psi prime. And I leave it as an exercise to you to show that the product of two unitary matrices is also itself a unitary matrix. So because of this, we could actually consider this product here of C and B as just a single unitary matrix, and it's almost as if our qubit isn't passing through two quantum gates, but rather one quantum gate, and we just have two gates in our diagram just for convenience and clarity. So this was a lot of technical information that I presented to you, and you should know all of the mathematics now about single qubit circuits. However, I want to place this in some context. What does this mean for us as computer scientists? How can we think about quantum circuits as computers? So we can think about qubits as data registers. Remember that we've shown a qubit can encode two real numbers. and we can take this data and feed and use them to parameterize a qubit in the following way. And we can show that a very easy way to visualize this is as a point on the surface of a three-dimensional sphere, aka the Bloch sphere. We can think of quantum gates as data processors. When we apply quantum gates, we are modifying this encoded data. And although I didn't prove this to you, you can think that through a combination of a few parameterized quantum gates, we are able to modify a qubit with an initial state of the zero ket or any initial qubit state to reach any other point on this Bloch sphere. And finally, we need some way to recover this modified data. And this is a bit challenging because we can't observe the modified data directly. Instead, we have to make a measurement using this observable matrix. And this measurement will collapse the qubit. And what this means is that if we want to compute some statistics about the circuit, for example, the expected value, and we want to compute it accurately, the entire circuit has to be set up and rerun many, many times. So we can't just run the circuit once and know an expected value. We have to just perform the entire circuit again, all of the unitary transformations that we would like to apply in order to take another sample. Additionally, we have this very interesting result, which is that if you compute the if you look at what the expected value of the Pauli Z matrix should be, it should be equal to the cosine of theta, where theta was used to, theta is the same theta which parameterized our qubit psi. I leave that to you as an exercise to work through. But what this means, this is much clearer to see on the Bloch sphere, but what this means is that if we are measuring the expected value of a qubit using the Pauli Z matrix, what we are actually measuring is a projection of this qubit onto a unit vector pointing upwards in the Z direction. And if you work through the mathematics, you can see that we actually have symmetric results for the Pauli Y and Pauli X matrices, namely that if we take an expected value with the Pauli Y observable, for example, it should actually be the projection of this point on the Bloch sphere onto the unit vector pointing in the positive direction on the Y-axis. One last little aside for this section before we wrap up and move on is that I've introduced two different classes of matrices here. We have Hermitian matrices and unitary matrices. Neither one is a proper subset of the other. However, there are some overlaps between these two classes. So here in this Venn diagram, you can see, remember, a Hermitian matrix is equal to its own complex conjugate. It's used for measuring a qubit. A unitary matrix has its inverse equal to its complex conjugate, and it's used for transforming a qubit with aka representing a quantum gate. And in the middle, we have all of our Pauli matrices. They are both, it can be both used to represent a transformation and be an observable. And just for another example, I also included I as a matrix that falls into both of these classes. Okay, that concludes our section on single qubit circuits. I think that this would be a natural point for a break. I would say, just in the interest of making sure we have enough time, maybe 7 minutes or something. Yeah, but let's go for a 7-minute break. And then we can move on to talking about multi-qubit circuits and then close with an outlook on quantum machine learning.